All right, everyone. How are we doing today? Must more like everybody else, I guess. Tired, but doing okay. All right, class. Class is quiet today. That's all right. Okay, so the plan for this week is to cover 2.5 sections, we'll say. Um, Last week we introduced the beginning ideas of section 15.3, which has to do with polar coordinates, and I assigned the quiz for the material from sections 15.1 through 15.3, but you have until I think, the end of the week, either Thursday or Friday. I think I made it Friday. I forget. Maybe it's Thursday. Anyway, because a couple of questions on the quiz have to do with 15.3, which we're going to talk more about today. And then we'll also, by the end of the week, also talk about 15.4 and 15.5. Okay. We're going to spend a little bit of time with 15.3 and then transition into those other two sections. You will have until after spring break to complete the quiz over the material that we covered this week, excluding 15.3. I don't want to make something due on spring break. That seemed silly. And then after we come back, we will finish chapter 15. In the syllabus, it says we're going to be covering 4 sections, but we're really only going to be covering 3 because we're going to cover most of the material from 15.9 concurrently with the material in the sections, as opposed to doing that all as its own separate thing. Okay. In the textbook, they break it down into a separate section. I don't think that's a helpful way to handle it. So we're going to do things a little bit differently. Okay. Polar coordinates. There are a couple of classes of domain. Something like that. They're supposed to be circles, but I'm not gonna. The command to try to make them square or conform to shape is not quite working. Anywho, these domains have radial symmetry. Okay, that's what makes them special. And the thing that you should be looking for when it comes to deciding whether or not you should employ polar coordinates, once we have a good idea of what that looks like, is if you can start at the origin, extend a line out from the origin, and then sweep out the shape by rotating that line. Okay? Now, as this is going on, this line is allowed to change length. Okay? It also doesn't necessarily have to start at the origin, right? But the idea is that when it moves, it has to move like this. Okay? So, a domain that is shaped like this would be fine, assuming that these edges line up with an origin. Okay? And so that is what we're going to be doing. Okay? Now, when we set up polar coordinates, the thing that is required is a transition formula that tells us the relationship between the coordinates. We have a couple of formulas. This is how we express x and y in terms of r and theta being the coordinates for polar coordinates. And r is defined, the square of r is defined as x squared plus y squared, and r is going to be strictly non-negative in this coordinate system. Okay? Well, okay, sorry, that's not true. Want to be more careful about how I say this. When we integrate over domains, we want to construct our domains typically so that r is strictly non-negative. Okay, so it has to be 0 or greater. In polar coordinates, however, it is possible to have a negative value for r. All right, but that has to do more with drawing polar curves. That has to do with thinking about r as, or using r when we're talking about integration. Okay, so typically what you do, if possible, is parameterize your domain that you're integrating with so that r does not take on negative values. We don't want r to be negative. Okay. What you would do instead of having a negative value for r is manipulate the range of theta values that you are integrating over so that that doesn't happen. Okay. This is one of the subtleties versus of talking about this in terms of area as opposed to working with curves. Okay. In calculus 2, when you talked about polar coordinates, you were doing basically space curves in 2D under that coordinate system, right? That's basically what was going on. You were graphing a parameterized curve. This is not what we're doing here, okay? We are describing an area using this radially symmetric coordinate system, which is why we have to treat r slightly differently, okay? No. The two lines here for the sets of equations. The first is how you convert x and y to r and theta. And the other one, the other line of equations is how you convert the other direction. Or yes, yeah, it's the set of equations that gives you all the relationships that you need to have between the x variable and the y variable, and r and theta. Well, there's one more piece of information you need to set up the integral, but these are how you change from one coordinate system to another. Now, this we have to be careful about, okay? Because arctangent does not necessarily give us the correct angle. Okay? Whenever you use the arctangent function, you have to be careful about making sure that you're in the correct quadrant. The base behavior of the arctangent function is to map things from negative pi over 2 to pi over 2, right? Sometimes you have angles in quadrant 2 or quadrant 3. And so you have to do the adjustment to make that happen. I think that the easiest way to remember how to do this is to use reference angles. Okay, you have this theta here, right? All of these angles are theta. If you're in quadrant 1, I'm going to put a tilde over this, okay, to indicate that it's the reference angle. All of the indicated angles are equal to the reference angle. And the true angle is this one that's made with the positive x-axis. In quadrant 1, theta is equal to the reference angle. Okay. In quadrant 2, theta, which is this angle, is equal to pi minus the reference angle. Quadrant 3, it's equal to pi plus the reference angle. And in quadrant 4, it's equal to 2 pi minus the reference angle. What's nice about having this in terms of the reference angle is that if you take the absolute value of the arctangent of y over x, you always get the reference angle. So that's how you break this thing open without having to play a bunch of games with angle measures and stuff like that. Okay, this is the approach that will always work. Okay. Questions so far? Okay. I know this is a little annoying, but this is what we have to know to be able to find our limits of integration with respect to theta. Okay, that's why this is important. All right. Now, in the online notes, and we talked about this before the weekend, I went through the description to show what happens with the scaling factor and the fact that ultimately there is a difference between a polar rectangle and a regular rectangle. And if we set things up and do things in an equal way that shows what happens to the coordinate systems as we switch from one coordinate system to another, there is a necessary scaling factor that is introduced, which is this r here. Okay, so when we set up an integral in polar coordinates, if we have a function that's given to us in rectangular coordinates, or if we're just integrating in rectangular coordinates in general, it is necessary for us to introduce the scaling factor to the integrand. Okay, it is a property of the coordinate system. We operate kind of on an underlying assumption that the x and y coordinates are the base coordinate system. It is the canonical coordinate system that we work with. So integrating with respect to any other set of coordinates is going to introduce a scaling factor. So let's do an example. All right. Integrate x squared y dA over a region D. And this is going to be the top half of the disk of radius 5. What we want to do here is make a sketch of the domain. It says it's the top half of the disk. Okay. It says our radius is 5. Okay. And what we want to do is set up our interval. So the way that this is going to work is that we are going to integrate like this. We're going to start at the origin. We're going to go out here to R. Start at the origin, go out here to R, and then sweep through like this. Okay, that's how I want you to imagine things working out. Okay, if we do that right, then this whole area would have gotten filled in. Okay, so set up the integral. What we do is we change coordinates according to our formulas. All right, we have x equals r cosine theta and x equals r sine theta. Theta is the angle measure, so it's the rotational part. Yeah. So this is r, the distance away from the origin. Theta is the angle measure, starting at the positive x-axis and moving this way. Okay. So we want to set up our integral here. The first thing that we need to do is replace replace x and y with r cosine theta and r sine theta, respectively. And importantly, we need to change dA to r dr d theta. It is multiplied times the integrand. So it's a normal multiplication. It doesn't get multiplied to both. You don't use the distributive property or anything like that. It's just multiplication. Yes. Yeah, no. It's just there's an extra factor of r in the integrand. Okay. Now, what we haven't done yet is figured out the limits of integration. In this case, it happens to be pretty easy. Okay. Our angle goes from 0 to pi. Right? Our radius goes from 0 to 5. Okay? So this gives us the equivalent of a rectangular integral for polar coordinates here. I have 4 total factors of r, excuse me. 2 here, 3 and 4. Okay. So the function that I need to integrate is r to the 4th cosine squared sine dr d theta. Now, there are a number of things that we need to make sure that we are training ourselves to do when it comes to looking at integrands and figuring out the easiest way to evaluate them. Okay? I look at this right away and notice that the integrand is separable. A separable integrand means that it can be written as a product of a function that only depends on one of the variables times a function that only depends on the other variable. So there is a function of r here and a function of theta here that's being multiplied together. This makes it easier to evaluate the integral because I can separate the integral into a product of integrals. You don't have to do this. You'd get the same answer. It's just this is something that is fairly common in polar coordinates, so it's helpful to look for to clean up the writing that goes on. Okay. You'll do a bunch of problems where the theta part becomes its own integral. It's just a pattern that you'll notice if you're looking for it. You wouldn't know to look unless I told you, though. Okay. So we can use the property of separable integrals to rewrite this as the product of integrals. Okay. If you evaluated the integral without doing this, you would get the same answer. Okay. But we'll write it like this. Separate it, multiplication. If it was a minus signs, it'd be much more pronounced than that. All right. So we'll do the magenta integral first because it's easier. Increase the power by 1, divide by the new power. what's 5 to the 5th power? And divide by 5, right? You just get 5 to the 4th power. Okay. Okay, so that's the first one. For the blue part of the integral, pretty obvious u substitution here, right? That u equal to cosine theta. Du equals negative sine theta d theta. Cosine of pi is -1. Cosine of 0 is 1. And so we end up with negative u squared du integrated from 1 to -1. We can absorb the minus sign, switch the limits of integration. I absorb the minus sign into the limits of integration, which means I can, if you switch the limits of integration for an integral, it introduces a minus sign. So, yes, the property of integration. I did it to remind you that you can do it. This is going to be 1/3 minus -1/3. We get 2/3 here. And so our integrand overall is going to be 1,250 over 3. Which doesn't reduce as a fraction, right? Okay. So, what do we think? Seems okay? All right. When you integrate in polar coordinates, you have to have the extra r. A fact of integrating in other coordinate systems is that there will always be a factor that is introduced by the change in coordinates. Okay? So, here's the inside baseball of this. And then, by the way, those of you who are listening to the recording, there's a tornado siren or something or that's going on, or my hearing is going bad. Okay. Anyway, so if that's coming through the mic, I apologize. It's not something I have any control over. Either my tinnitus was flaring up really badly or something else is going on. Anyway, so on screen here, I've indicated the substitution that we have done for the u substitution that we used to solve the integral. Now, you weren't told this in Calculus 1 or Calculus 2, probably, but the truth is substitution is a change in coordinate system. Okay, that's fundamentally what's going on. The reason that we do the change in coordinate system, which you probably were told, is this is how you undo the chain rule when it comes to integrating functions, right? U substitution is essentially the inverse process of performing the chain rule. But from a mathematical perspective, what's going on is we are reparameterizing the problem into something that's easier to deal with. Okay? This reparameterization is a change of coordinate system, and this change of coordinate system introduces a scaling factor. Okay? This right here is the scaling factor that is the result of changing from u to changing from cosine theta to u. All right? Just like a factor of r is the necessary scaling factor that is introduced when we change from rectangular coordinates to polar coordinates. Because this factor here has to be part of the integral. It serves the same purpose. Okay? We don't introduce the idea of a Jacobian, which is what I'm talking about, in Calculus 1 because that adds some extra complication to things. And it also doesn't make sense to talk about a full Jacobian until we are dealing with more than one independent variable. Okay? But when we have a higher number of independent variables, we ultimately need that scaling factor to reduce to a function, not some vectorized thing. So we will, as we go on here in the other sections, bring this idea up for how it comes up in other contexts. All right. I want to make sure that we have plenty of time to talk about subsequent sections, and we will end up doing more polar coordinate integrals in 15.4 and 15.5, just as those problems are set up and how they work. But I do want to do a small demonstration here. Not the best artist, but imagine that's symmetric. So here we have a poorly drawn clover leaf. Actually, it's really bad. I'm going to fix it. Okay, that's not as awful. Anyway, I have a tiny amount of pride when it comes to my drawings, but I know that I'm terrible at it. There's a reason that I do maths of art. Anywho, not for me. The only like minorly artistic thing I ever had any, I wouldn't call it talent, but we'll say aptitude for was essay writing. Like, I write essays okay and like stuff like that, but not drawing, not sculpting, not music, none of that nonsense. Anywho, for a shape like this, one of the things that you can do using polar coordinates would be to find the area of one or more leaves of this shape, okay, or other similar polar curves. If you were told that the radius is given by the function cosine 2 theta, okay, that defines where you are on the outer part of the leaf here, okay? So if you wanted to find that area, what you would do is you would integrate we'll fill it in so that we know what we're doing. We'd integrate the function 1 with the appropriate limits. Okay. Now, of course, you have RD theta because we're talking about integrating in polar coordinates. But you set up the integral by integrating from negative pi over 4 to pi over 4, which is what you would find those angles to be for the polar curve. And then on the interior, you integrate from 0 to the edge of the polar curve, which is cosine of 2 theta. Okay, does that make sense? 0 to 0. So it's there's no length to the radius. So you're at the origin. Yes. So if I have a disk, it would go from 0 to whatever the radius of the disk is, right? If I have an annulus, it starts at the interior part of the annulus and then goes to the edge. So there would be an R1, which is the bottom part, and an R2, which is the outer part. Okay, so when R is 0, it means that we're all the way at the origin. Do you have a question? Yes. It is 0 to R. Okay, so the way this is set up, to clarify, because we have two integrals here, and I used the word first and second from the person I was talking there for a second, but I want to make sure that this is clear. The interior integral is the integral for R. Okay. The lower limit is R equals 0, and the upper limit is R equals cosine 2 theta. Okay. So that's how you think about how the interior part is going. That gives you the length of the line that you're rotating to trace out the loop. So it is going to fill in like this. Okay. Obviously, negative pi over 4 to pi over 4 is the angle that needs to be swept out by that curve. Does that help? Okay. So everything else for this example is just a matter of doing things computationally. R is easy to integrate. 1/2 R squared. Plug in the limits, then you'll get cosine squared 2 theta to integrate. And to integrate cosine squared 2 theta, you need to remember the formula for that, right? Cosine squared equals 1/2 times the quantity 1 plus cosine 2 theta. Except you have cosine squared 2 theta, so you'll end up with a 4 theta once you use the formula, but all stuff you can integrate. Uh-huh. The whole thing is how you find the area of a single leaf, not just the interior. This is this area. You need both integrals. So the setup for this problem relies on the fact that if I have some region D, and I want to find the area of the region D, this integral will tell me the area of D. Okay? That's why I wrote this. We're integrating the function 1. We have an r because we're integrating in polar coordinates. That's where the r comes from. But we're integrating the function 1 over the area that we want to, over the region that we want to find the area of. Does that make sense? Yeah. If I asked you to do, if I asked you to find the area of the entire clover, then you could just do 1 and multiply by 4. Okay. Let's talk about 15.4. All right. Now, 15.4, I will tell you right off the bat, is a section that is best handled by going through and reading the examples that are in the textbook and online, because there's a lot of physics to set up and it's a lot of material to digest, and I would have to spend more than an hour explaining all of the details for how these things go together. It's much more efficient if you read it. Okay, so I'm going to focus on the highlights. All right. The couple of applications for what we're doing here is, now that we understand how double integrals are constructed, is if we have some shape. Pick something easy here. Okay, so this is some domain D. Now, D is going to be a lamina of non-uniform density. What that means is that it's going to be a thin sheet of material. You can think about it as a thin plastic, or maybe a thin silicon wafer if we want to use an application for computer chips or computer hardware, something like that. Okay, it is so thin that I don't really care how thick it is relative to its other two dimensions. In engineering, there is the concept of one-dimensional or two-dimensional materials. Okay, if you're talking about engineering and you have, say, a wire, okay, or a piece of rope or a piece of string, it very rarely matters what the radius of that object is, right? The only thing that you really care about is how long it is, for the most part. In most applications, you just assume that it is infinitely thin most of the time you're going to be talking about, okay? Or the kind of rope that you get from the magic physics store that you use in all the pulley problems that are the frictionless ropes, right? Okay, those things are one-dimensional materials because length is the only parameter that matters. Here, for lamina, this is a two-dimensional material. We care about its area, but its thickness is irrelevant. Okay, it's so thin that the problem doesn't care. All right, but unlike when we attacked these problems in Calculus 2, where we assumed that the lamina had a uniform density, we are going to assume that there are variations to the density, fluctuations, because that makes the problem harder and we couldn't handle it back in Calc 2. But now we know what we're doing. Okay, so what we can do is we can ask ourselves questions like, what is the center of mass? Okay, depending upon the density of this object, we should be able to find some point here that represents the center of mass. Okay, now, if it were a regular old triangle of uniform density, the center of mass is always the centroid of the triangle. But that's not necessarily the case because this triangle is allowed to, say, be really thick on this side and thinner as it goes to the right, for instance. That would affect the placement of the center of mass. The way that this is going to be set up is we use formulas for moments. Okay? The mass m is going to be given as the integral over d of the density function. Okay? Now, in Calc 2, rho was just a constant, right? That's the difference. Here it's allowed to be a function because we can do double integrals now. The center of mass, it's not an F, it's a Greek letter. It's a kind of funny looking R. Some people write it like this. But the Greek letter is named rho. It is the typical letter that you use in math and physics when you're talking about density. I try to make my Greek letters look really exaggerated and unique so that you always know which one I'm writing down. Okay. Now, the notation that is used in the text for the coordinates of the center of mass are x bar and y bar. Okay. Over bars are typically used in math and statistics to indicate some kind of mean. Okay, since we're talking about a center of mass, which is the location where the average moment occurs in a a body. That's how this is set up. Okay. So what is meant by ultimately what we want to compute here is a moment. Imagine that I have one of these lamina, and this lamina is sitting on top of a pointed object. Okay, I'm trying to balance this lamina on this pointed object. Okay, so in a one-dimensional version of this problem, you would have something that looks like a teeter-totter or a seesaw, depending on what part of the country you're from, or neither of those things if you're not from the US. Anyway, it's a children's toy, right? You have one kid sitting over here and another kid sitting over here, and they're rocking back and forth, right? And the idea is that they apply rotational forces to this object moving around the fulcrum, which is this piece here, right? And the length of the legs of the teeter-totter and how massive the kids on the toy are affect how much the thing twists around that fulcrum, right? This is a moment, all right? Same thing's going on here. This plate has mass, okay? And that mass is applying moments on the fulcrum that this thing is sitting upon, okay? The farther away from the origin, the larger those moments become. And that is how we're dealing with this object here, trying to find the center of mass. In order to set this up, what we're doing is we are treating each of the coordinate axes as a thin, infinitely long fulcrum that the plate is applying its forces to in the horizontal direction and then in the vertical direction relative to our perspective. Okay? So there are moments that depend upon the distance away from the x direction, and there are moments that depend on the distance away from the y-axis. Okay? Does this make sense? All right. The moment is the rotational force being applied. So it's the moment is how much the plate is trying to rotate. If it is supported at exactly its center of mass, all of the rotational forces are balanced. So the thing will stay upright and level. Okay? You've all seen that bird toy that has like the big wings that swoop out in front of its beak, where if you put your finger underneath its beak, it'll balance there. It's because that toy is designed to have the center of mass be directly beneath where the beak sits. Okay? That's what we're doing here, is we are mathematically setting that problem up. So the elements of the mass that are away from the y-axis are going to contribute to the location of the x coordinate for the center of mass. And the elements of the mass that are away from the x-axis are going to contribute to the y location for the center of mass, because of it's the moments trying to twist the thing. There's this kind of twisting, which tells us where the location of the x coordinate for the center of mass is, right? And there's this kind of twisting that tells us where the location where the y point for the center of mass is going to be. Okay, we need to compute those separately, and we're going to use the fact that theoretically adding up a bunch of different points all on the same body can be handled by computing an integral. Okay, because integrals are really just summation, right? It's what happens when you turn summation into an infinite process. that's how integrals arise. Now, the way that these things are defined, the letters are a little bit mismatched. So do be wary of that. The location of the x-coordinate for the center of mass is given by the moment in the y direction divided by the mass. And the way that the formula for that looks is that it's the integral over the double integral over d of x times the density function dA. We have an equivalent formula for the location of the y coordinate for the center of mass. It is the moment in the x direction, or it's the moment about the x-axis, excuse me, divided by mass. Okay, so in general, to solve this problem, if I ask you what the center of mass of a lamina is, you are going to need to compute 3 integrals. The first thing you do is you find the mass of the lamina, and then you find the moments about the x and y axes. Make sense? Okay. All right. And then just so you know, and so you have something to follow along with, there are examples here on the online notes that I suggest that you check out that go through and in more detail and a little bit more carefully than I was talking about here, explain these ideas and provide examples for you to follow along with. Okay. And then the other idea that I want to talk about today, to make sure that we understand what's going on here, because conceptually, without moving pictures and physical demonstrations and things that you can manipulate, it's a little bit hard to get these ideas quite right. All right. Now, what we just finished talking about having to do with the moment of inertia, or sorry, with finding the center of mass, was computing something that is known as the first moment. Okay? Whenever the idea of a moment comes up in a physics context, which is underlying what's going on here, we're talking about that idea of rotating whatever shape it is. Okay? The first moment has to do with making, in some way, rotating the object with respect to itself. Okay? Trying to find the balance point of the object. Okay? We measure that with how the object is oriented with respect to the origin, but that's the basic idea. Now, there is another concept that you may have interacted with if you have taken physics, which they've changed this since I was an undergraduate. You used to be able to take Calc 1 and Physics 1 at the same time, but I don't think they let you all do that anymore, do they? Yeah, they threw us to the wolves. The problem is it doesn't usually become a problem until you get to Physics 2, and then they realize that nobody knows Calculus 2, and it's a mess. Anyway, however, we probably talked about moments of inertia. Okay, Except for moments of inertia, they probably just gave you a table and said, hey, use this, right? Okay. The moment of inertia of things like if you have an annulus and you want to rotate that annulus around the origin, or if you have, say, a solid bar or a solid round rod, what that's like to rotate either along the longest axis, so it looks kind of like a spinning wire, or an axle, I guess would probably be the best way to, the way that you would use an axle, the way that you would want to rotate it, right? Okay, and then the other way that you can spin along a rod like that would be how you would say spin a quarter staff if you were doing martial arts, right? Different types of spinning. One is the type of spinning that you were trying to do if you're using a stick to start a fire, okay? The other kind of spinning is what you would do if you're trying to hit somebody with a martial arts weapon, okay? Those have different rotational properties in how hard it is to rotate the object. It takes more energy to do one of those than it takes to do the other one. Which one takes less energy? Rotating it like an axle, right? The motion that you would do to try to start a fire. It's easier to rotate it along the axis where most of the mass aligns, right? If you are rotating it along an axis where the mass doesn't line up, then it requires more force in order to overcome inertia and move the object. Okay? This is the nature of the second moment. Okay? The way that we figure out what the moment of inertia of an object is, which fundamentally is how difficult is that thing to rotate, how hard is it to rotate that body, we can compute that now. Okay? And the way that it's computed is relatively simple compared to what you would think. There's just an extra factor of x and an extra factor of y in the appropriate integrands in order to get the second moment, which is why they're called the second moment. Okay? So right now, we're still only working on two-dimensional objects. The examples that I spoke about out loud here were 3D because those are the easier ones to conceptualize. But if you have a lamina, we can compute its moment of inertia. Okay, how hard is this object to rotate around the x-axis or around the y-axis based on its positioning? Okay, because the moment of inertia will change if I slide the object. If I translate where the region D is, that changes the moment of inertia, just like it would change the mass or the center of mass, right? Okay, now translating the object has a more pronounced effect on the moment of inertia than it does on the center of mass, because the center of mass just gets translated by whatever the translation is, right? If I move this thing away from the origin, it becomes a lot harder to rotate, right? So mathematically, we can set things up in a way that makes sense with the fact that we now understand how double integrals are computed. Okay. The moments of inertia here do have one additional wrinkle in that we also care about something called the moment of inertia about the origin, which in your physics textbooks, the formulas that were quoted to you about the moments of inertia of those three-dimensional objects are the moments about the origin. Okay. It's the rotational difficulty of rotating it in the XY plane. So if I were trying to rotate this way, like spin the region D so that it remained flat, that's this. Okay? The moments of inertia with respect to X and with respect to Y are me trying to rotate the region D into or out of the page about the appropriate axis. So if I imagined that D got stuck to the x-axis and I was trying to spin it around like this, so that you would see, like, D would push air, right? If it were spinning along that axis, okay? And then the moment with respect to Y would be spinning it this way. Okay. I know this is hard to imagine, especially with me just talking, but uh, I've tried to make computer demonstrations of some of these things. It is a matter of not being a professional artist, and that includes generating computer graphics. Kind of tough. Never learned the animated 3D animation studio stuff. Maybe. I know. That's why we're talking about it. And I'm also referring to the notes. The thing that I hope to impress upon you is enough of the understanding so that when you go to compute these things, you know what you're doing, or you know what you are computing. Okay? Now, I can't do the practice of integrating enough integrals for you to give you that skill. Okay? That's part of the reason why I'm not dedicating class time to doing absolutely as many examples as possible. All right? Because that's your job. Now, I'll help. I'll show you how to do things. We set up a couple of polar integrals today and talked about some of the things that can happen, right? Like reminding you, for instance, that you're going to have to remember your trig formulas, okay? Because sines and cosines are going to show up in those polar coordinate integrals, and all of a sudden you're going to have to remember all the stuff about how to solve integrals via trigonometric substitution or using trig formulas that you probably immediately forgot after that test in Calc 2, right? Okay, well, it's back, all right? And just so you know, all of you who plan on taking differential equations someday, when you take differential equations, you will have to use everything. And I mean everything that you learned in Calc 2 in that class. All of it. All right? So don't try to compartmentalize or flush down the tube or whatever it is you're doing with that integration knowledge. You're going to need it. Okay? All right. There's one other interesting application here that I want to touch on so that we understand some things that can be done with integrals other than just computing stuff. Okay, there's an important connection to statistics that comes through integration as well. In a lot of ways, even though we're not used to thinking about this probably because we imagine, or at least a lot of us probably think that statistics has to do with some kind of counting, either be it I don't know, card counting, maybe might be the most fun thing that you can think of doing with statistics, right? How many people have like studied or spent time learning the inner workings of casino games? A little bit. Okay, that's all statistics, right? It's if you're playing poker, knowing what hands are good to win with, what hands are not good to win with, understanding the probabilities to the extent that you can adjust your betting based on how likely you are to win, right? Because when you're playing a casino game or any other type of thing, this also extends to other things that are related to card games, like you happen to be someone who plays Magic the Gathering or some other competitive card game, the way that you evaluate your decisions goes together in the same way, all right? You change your strategy based on something called an expected value, okay? Your decision-making process you're not always going to make the right choice based on the situation. There's going to be a probability that you are making the correct decision. Your goal should be maximizing the percentage of the time you make the correct decision, not changing how you act based on whether or not you got lucky that time. Okay? So if you make a big bet and you win, but you had a hand that was only 12% likely to win in that particular scenario, you made the wrong choice. It doesn't matter that you won, you did the wrong thing, because you're going to play 20 more hands, you're going to make more of the wrong decisions, and then lose your butt on the rest of whatever money you made, and maybe if you're a bad gambler, have gotten into your pockets and lost more. Okay? Making those kinds of evaluations is the real way that this is dealt with. Okay? Now, these things can be modeled using mathematics. Okay? In mathematics and statistics, we can figure out something called an expected value. Okay? If you have independent decisions that are represented by the variables x and y, okay, and a probability density function, which is represented by f of x, that incorporates the relationship between when decision x and when decision y, or when result x and when result y are coordinated, and when those two things are both likely to produce positive results. You can figure out by evaluating integrals that look an awful lot like the first moment integrals that we use to find the center of mass, to figure out what the most likely set of outcomes are for a particular range of values. And what you can do is you can cut the range of values that you're integrating over to some subset of the coordinate plane in order to figure out what the most likely value is, or what the probability is for the result of x to, say, come up to be greater than 1/2, or what is the probability for x to be greater than or equal to 1/2 and for y to be less than or equal to 1/2. And so you can chop up the ranges and figure out what percentage of the time a combination of events are likely to occur. This has far-reaching consequences into all those things that I was just blabbering about. Okay? And it's based on a relatively simple mathematical framework that you all now should understand most of, even if you haven't had a lot of practice with it. Okay? It's just evaluating a simple double interval. All right? A joint density function is a function that incorporates the probabilities of two independent events into a single function. Yes. Yeah. The joint density function is basically the equivalent to the mass density function from the center of mass examples that we did before, except instead of how thick the object is or how massive it is, we're talking about how likely a combination of events are to occur. So it's just a probability version of that computation. All right, take care, everybody, and I will see you next time.